Let's start. It's day 2, 17:15, and the next talk is about just-in-time compilers breaking a virtual machine. These two guys took Kakao, built some code generators for it, spotted that there are vulnerabilities and fixed them. And the talk is about their findings. Have fun and welcome Roland Litzuo and Peter Mollner.
Hello, I'd like to welcome you to this lecture about just-in-time compilers and how to break a VM by attacking its just-in-time compiler. Who we are, we already introduced. My name is Roland Litzuo and this is my friend Peter Mollner. And we both developed code generators for the Kakao virtual machine. And during development we saw, you can do many things wrong in a just-in-time compiler. And said, yeah, let's look at this and make a lecture for the CCC out of this. In this lecture we will give you a short introduction to Kakao, what is it, and we'll then switch to an introduction in just-in-time compiler and tell about some interesting implementation details. And we'll then come to the main important point of this talk, security in just-in-time compilers, where can go things wrong, where to exploit stuff, where to look for. And we then did a code review of the Kakao virtual machine and we'll tell you what we found there and show you some exploits. Okay, Kakao is a Java virtual machine and I think you all know this, but it executes Java bytecode. The Java language is compiled into bytecode by the Java C compiler, which is machine independent. And on the host system or on the desktop computer or wherever a Java program is run, just-in-time compiler or interpreter, but in our case just-in-time compiler, comes in place and translates the bytecode into machine code, which then gets executed. Kakao is free software, it's GPL licensed, and it's available for 10 hardware architectures and 4 operating systems. Not each hardware architecture has each operating system, but so it's a highly portable Java virtual machine. Kakao uses a just-in-time compiler for performance and we're quite fast. And we use only just-in-time compiler, so there's no interpreter, so everything is compiled. What is a just-in-time compiler? Just-in-time compiler, the counterpart of a just-in-time compiler is a ahead-of-time compiler. This is what we all know when developing at home, compiling a program into machine code for one hardware architecture and one operating system. And the binary can then be executed on computers of exactly this type. And for just-in-time compilers, the idea came, why not use a higher representation, the bytecode, and compile it to machine code directly on the PC. So the developer can ship just one binary, which can be executed on many different architectures. Another observation was that many code inside a binary will not be executed at all. Just think of error handling cases. When the error does not occur, the code is never executed. And this is something a just-in-time compiler tries to use, and the method or code piece is compiled directly before it's used for the very first time. So when the method is executed or about to be executed, the compiler kicks in, generates the machine code and executes this. In the program there are always some methods which are executed very frequently. These are so-called hot methods and they are normally compiled with an optimizing compiler which takes more time. And thing is, code has to be generated quickly, that the execution time of a method is not too high. As you can imagine, there are some interesting implementation techniques necessary to implement a just-in-time compiler. One thing which is rather interesting, when the compiler kicks in. Look at the diagram and assume method A is already compiled. This method A will then call or invoke a method B. And there happens a normal Java method invocation which says basically branch to some address where this method is. But at this address there is no method, there's a compiler stub. The compiler stub has been generated when the class was loaded. For each method, the compiler stub is generated then. And the compiler job invokes the just-in-time compiler, which takes the bytecode of the method to be executed compiles it, places it somewhere into memory. The entry address of the method is different from the one in the compiler stub. And one job the compiler stub does is to replace these method entries in method A, which already invoked the compiler stub, with the newly generated address of the method P entry point. So we have runtime code modification. We modify the code during runtime, which means write, or execute cannot be implemented when using a just-in-time compiler, because just-in-time compilers in normal cases modify their code. The compiler stub further manipulates the stack so that its call frame is removed from the stack and then executes method B, which returns normally, and because the compiler stub has been removed from stack, we're back to method A. So it's completely transparent for method A. It does not notice there was a compile process during execution of method B. If there are any questions, you can always ask. When generating code, it always comes down to ORing together bit fields. That will be important later when we talk about the exploits, because we almost always have some integer overflows. Here you can see a rotate left double word then clear right instruction of the PowerPC 64. This instruction is said to be Turing complete, and it could be true. In the first line you see an assembler memo of these instructions and the arguments. And the color corresponds to the bit field inside the fixed 32-bit instructions encoding used on PowerPC 64. And this line here is a C macro used to generate the bit field from the arguments of the instruction. It was quite hard to get this one right, because there are many subtle details for this instruction. Another very important aspect for just-in-time compilers is that the information needed to compile the code is not always available when compiling the code. Sounds crazy, but Java demands lazy class loading. It's a kind of optimization. So if you have a method and you invoke a static method of a class, and the class has not been loaded yet, the entry point of the method is unknown. And in Java, you cannot load the class when such a method is compiled, but you can only load the class when the invocation of the static method is about to happen. This could be if the invocation is in an if branch and the branch is not taken, the method will never be invoked, so the class will never get loaded. This is rather hard part, and in Kakao we use something called patchers. When we generate the code, and you can see invocations of a static method on the upper left side, we load an address from somewhere and then branch to this address. That's the call register R10. And from somewhere we loaded the address. In case we did not know the address yet, because the class has not been loaded yet, we need something called a patcher. So we overwrite the code generated with an illegal instruction. That's the UD2A instruction on the right upper side of the slide. And when executing these instructions on the POSIX operating system, an illegal instruction signal will be sent to the process. Kakao catches this and says, oh, probably a patcher is about to be executed, and looks up in a table if on this position there's a patcher. And when there is one, the class gets loaded, linked in the memory, compiler stubs get generated, things like that. Afterwards, the memory is overwritten with the original contents of the instruction, and the address of the method to be executed is inserted. And execution is then continued at the point where the illegal instruction occurred. So it's completely transparent to the program that class loading took place and things like that. Okay, now to the important question. We've seen such a JIT compiler does many nasty things, but what can a JIT compiler do for hackers? Let's try to look at it from this point of view. The input to a JIT compiler is complex data. It's Turing complex data, so it's rather complex data. The just-in-time compiler takes this input, makes a transformation, and outputs Turing complete data again. So that's a rather difficult transformation. And the best thing is, the result of the transformation will be executed. So probably we can have some fun here. Additionally, some just-in-time compilers are on highly exposed places. Let's think of a Java applet. It's loaded in the Java interpreter in your browser. ActionScript and JavaScript are executed by a just-in-time compiler called Tamarin. It will be in the upcoming Mozilla releases. Microsoft Silverlight's technology, Flash applets. There are JITs everywhere, and we can give them our data. And there will be more JITs in the future. But there's a big problem for hackers when they want to exploit such stuff, because just-in-time compiler fork have really huge test cases. You call them programs, we call them test case. So we have such insane big test cases like Eclipse, Tomcat, or JBoss, which do many nasty stuff, and the just-in-time compiler is really almost bug-free when it runs Eclipse. So this is a really big test case. But nonetheless, there are attack vectors. We have tried to group them in 3 levels of seriousity, and the highest level were undefined behavior in language specification. For Java, there's no undefined behavior as far as we know, but just think of C or C++, double free, it's undefined behavior, can be exploited. So undefined behavior is always bad stuff, but in Java we don't know about undefined behavior. When transforming the Java language into bytecode, a transformation takes place. Question is, are there any problems when transformating stuff? And are there any quirks when mapping the constructs of the language to the bytecode, which is a much simpler language than the Java language? And of course, we can try to attack the generated assembler instructions. Are they always generated correctly, or are there some tilts? This were the stuff we were looking at, and yeah, we then did a 2-hour code review and found quite a few things. But it has to be said, a few things. First of all, Kakao is a research VM, so it was never designed to be secure. We execute programs on our development machines. Yes, so it was not a criterion, but it has to be said that each vulnerability we found is actually just a bug. It's the same thing like many software, it's just a programming error which will be turned against the programmer by a skilled hacker. Okay, I will now present the stuff we found and the source code, what it looked like, but before I come to this part, I want to make the point clear what's an integer overflow, because we found a lot of integer overflows, and therefore you should know what it is. There's a 16-bit value and 12 bits are red, but let's ignore them for now. Think of it as a counter. On the left side there's the binary representation, then we have the hex representation, and then a decimal representation. And the thing is, when you always increase the counter by 1, it starts to tick. And somewhere, and that's in line 4, we have a leading 0 and a lot of 1s. This is interpreted as 7FFF hex. And this is the biggest integer which can be represented by a 16-bit value. And when we increase the counter 1 more, an overflow occurs. It's just a normal binary addition, but the interpretation of the result changes because the most significant bit is a signed bit. And when it is 1, the number is negative. And so the next value is minus. And it's the smallest value representable by a 16-bit integer. And this is where the overflow occurs. And yes, when we increase the count again, another overflow occurs on the last 2 lines from -1 to 0, but in this case the 1 just drops out on the left side when adding it, and we are back at 0. A very interesting effect also occurs when this 16-bit value is tried to be stuffed into a 12-bit value. And this is what happens quite often. In line 4, you see the biggest representable integer in the 16-bit